Okay, welcome everybody. Sorry if there was some confusion about the emails this morning. I did actually transpose some of the lab sections, so I apologize for that. So section 1 obviously hopefully met this morning at 9 a.m. Section 1B will meet next week at 9 a.m. Section 3A will be meeting today at 3:30. Section 4A will be meeting at 6:30 today, and then the B's meet on the following week. Okay, so that is all. Right now, our currently scheduled live Zoom is for 12:30 tomorrow. If you cannot make that, you should have received a invitation or a poll inside of the group me asking for a better time. We're hopefully going to have 2 live sessions with the lab instructor a week. And then after that, you'll have to just watch the video and do the activities online yourself. But you'll still be responsible for taking the quiz on Canvas, and that'll be explained to you by your lab instructor. There's a quiz on Canvas that has a 20-minute time limit. And so but that's only open till Wednesday at midnight. So there is a certain urgency to at least communicate with your IA for the section 2. The ones that are meeting in class, you'll be taking it in class. The one and B, you'll be taking it in class as well, so don't worry about that. Only section 2, online section, needs to take the Canvas quiz this week online. Okay.
If we're online and we have other work, for example, I have work on Tuesday mornings. Is that going to affect our grade if we don't? Why?
No, we're trying to schedule it. So I have the IA looking for different, I'm trying to schedule it 2 different days at 2 different times for the live section. And then if you still can't make that because there was an error in the way this class is usually on Tuesday, Thursday. So it would have never been an issue because that would have been when the lab was scheduled. Unfortunately, it got moved to Monday, Wednesday somehow. And so we have a scheduling error. If you cannot make one of the 2 live sessions, that is acceptable. And you can watch the Zoom recording of it before you take your lab and before you take your quiz, because it has information in there for you. And then the activity itself will be uploaded to Canvas. So as long as you're turning things in every week on Canvas and taking the quiz every week in Canvas, then that should count for participation. Okay?
Thank you.
Okay, I still don't have anybody. All right, great. All right, so for this week, we're going to continue on with chapter 4 and 5. And you'll notice that I started 5, and we'll do 5 and 7. I skipped 6. Okay, 6 is chirality. I want the whole week to just do chirality because it's got some trickiness to it that I want to make the subtle points of it very clear step by step. So I want to do 2 whole lectures on chirality. And then that'll take us into our review on September 28th. And that sets us up for our first exam on September 30th, okay? And that will be a online top hat exam. Our first top hat mock exam, so that you can test your equipment and make sure it works, happens on, let's see, the 21st, September 21st, and I'm gonna have another one on the 23rd, another one on the 28th. Basically, it's a 5-question thing. Make sure that you can get in. If you have any questions, go ahead and contact Canvas support, and they should be able to help you. I've had, let's see, with this group here, about almost 200 students using the top hat, and it seems to have far less issues than the examinee does. So I'm hoping that by doing those 3 mock exams for no points, you'll have an opportunity without stress, make sure everything's working. And then I do have some workarounds if necessary. But we'll be doing that starting next week. Okay, so this week we have chapters 4, 5, and 7 to deal with, which means that chapter 4 is due tonight. I'm sorry, chapter 3 is due tonight at midnight. Chapter 4 will be due on Wednesday, and chapter 5 will be due on Friday. Okay, so that will get us through all the way up to where we are on the schedule, and then we'll do chapter 7. We'll start chapter 7 actually this week, but we'll finish it next week, and then we'll do chirality. Okay. Questions on what's due this week? The files should be up on Top Hat. I think they're all up on Canvas. The full slides are on Canvas, and the goal slides are on Top Hat. And let's see, everything else is already, yeah, set. Questions about administration? Okay, well, you guys are thinking about that and putting a question into group chat. I'm going to go ahead and share my screen and start talking about chapter 5. Come on. There we go. Okay. So we should get through 5 today and then maybe even introduce chapter 7. Okay. So to remind you of what's happening in chapter 5, okay, we've talked about how to name alkenes and alkynes and how to be able to do that. Yes, that is correct on the Zoom chat about when those are due. So the first goal in chapter 5, when we're talking about alkenes and alkynes, is we have to figure out how reactions happen. And so that's why I wanted to talk about reaction mechanisms. And then carbocations play a role in what the actual final product is. So let's see. I think there's an invitation on Canvas under announcements for the group me for this. You can look. There's also a forum on Canvas where you might be able to find that as well. Okay, so let's talk about reaction mechanisms again. There were 3 things we had to worry about, and when we talked about it, we wanted to draw this energy diagram, okay? So with this energy diagram, it's important to notice the different parts and pieces of it because each of them tell us something different. One tells us that we had more energy at the beginning than the end or the otherwise. The other one tells us that big activation energy, the bigger that is, the slower the reaction is going to be. The smaller that is, the faster that reaction is going to be. And then if there were 1 hump, we only had a 1 step in the reaction. And if there are 2 humps, it has 2 steps in the reaction. And so each step has its own individual activation energy. Okay, so these are the words that we wanted to define. Make sure you understand what the definitions of these individual words are. And I believe they're sprinkled in the homework as well, so you should get some practice there. Okay, but now I want to talk to you. There's 5 things that we look for when things happen in a chemical reaction, okay? We talked about acids and bases already, and so that's going to take a play in our first pattern. Whenever we do a reaction, there are 5 things that can happen, okay? Especially if we have something that is what we call acid catalyzed, we should look for the addition of a proton. You're going to transfer a hydrogen from your acid to the substrate. That's one pattern that we have. And the reason that you transfer that is to make the other species more reactive or make it such that it makes it a better leaving group, okay? So in the case we have here, we have a nice simple compound. This is just the same as the acid-base reaction we had before. And it was where we have acetic acid is fairly acidic, and we have ammonia right here that's acting as our base. And when we react it, we end up with the acetate ion and this ammonium salt. This ammonium salt right here is a weaker acid than acetic acid was. Therefore, it shifted toward the right side of the reaction, okay? So that's the first thing that can happen. And notice most of the time when you do this, you have some lone pair on the other compound that is accepting that proton and making a new bond. So that's what I want to draw your attention to right now, is that this proton right here, I'm going to draw attention to it right here, is being bonded to by these electrons on the base, okay? So that base, think about Lewis base, right? It has electrons that it wants to make a new bond with. And that's what's happening when we transfer that proton. Now, why might we want to do that? Well, now we have an anion here that can act as to attack something, okay? So it can act and try to attack something with a positive charge. So that's our first pattern. Add a proton to a system. Okay. The second one is take a proton away. Okay. So in this case, we have that acid-base pair, and we actually have the acid acting as our base now and using this lone pair to remove a proton from here, giving us back our free lone pair. Okay. So we might want to do that so that we can have those electrons act as a base somewhere else. So we can add a proton or we can take that proton away. And you're always looking for that lone pair as going to be generated when you take a proton away. Okay. So our third pattern is what we call a nucleophile electrophile reaction. Okay. So what we really want to think about this is as a Lewis acid, Lewis base reacting with each other. So an electrophile is an electron poor species that wants electrons. It loves electrons. That's what electrophile means, right? Which means it has either a positive charge or partially positive charge. And when you have that, you are, by definition, a Lewis acid. You are willing to accept a pair of electrons. So electrophiles are Lewis acids. They're willing to accept that pair of electrons. On the opposite side of that, we have what we call a nucleophile. This is something that wants positive charge. It loves positive charge, right? And these are classically Lewis bases. They already have a lone pair of electrons that they're willing to donate to make that new bond, okay? So anytime you see a positive charge reaching out and grabbing a pair of electrons from something nearby, that is this pattern here. That's the reaction of our electrophile with our nucleophile. And think Lewis acid, Lewis base, okay? Now, if you have those two things and they react to form a stable covalent bond, then your reaction's done. You know you've done it really well. Okay, so let's use that as an example here. So in this case here, instead of using something like, a metal or something, we're going to use an organic version of a Lewis acid. And the most common one of these that we're going to look at is what we call the carbocation. We're going to talk about more like that in goal 2. But the carbocation is a positively charged carbon. It wants electrons in its outer shell, and so it's going to act as that Lewis acid and accept protons from any Lewis base around. In this case here, we have chloride ion. It's a very weak Lewis base, but it has electrons to share. And so when it does, it forms the new covalent bond right here. So we had our Lewis acid react with our Lewis base to generate a new covalent bond. That's pattern number 3. Okay? So add a proton, take a proton away, have a Lewis acid react with the Lewis base. Electrophile react with a nucleophile. Okay? The next thing that can happen in a pattern, not all these steps happen in every one, but all of these patterns happen in the mechanisms we're going to talk about. So the next thing that can happen is we can rearrange, okay? Now, there's a driving force for rearrangement, and we're going to talk about that when we talk about carbocation stability in part 2 here. But the idea is that if you can move either a hydrogen or a methyl group to make a more stable carbocation, and we'll talk about that in a minute, it will. And so this pattern is called rearrangement, okay? And so what you'll end up with is, even if you started with your Lewis acid on this carbon here, by transferring either this over or this over, you can end up with your Lewis acid on a different carbon than you started. Usually it only transfers one carbon over, and you only move hydrogens or methyl groups. But that's the 4th pattern of things we can see in our mechanism. And in the next 2 chapters, we're going to actually see all of these, okay? The last thing we have is what we call a bond breaking, okay? So in this case here, what we're doing is we're taking a covalent bond. Normally it is a polar bond, okay? And you typically use it to make ions from it. But when you break this bond, the electrons that were forming the sigma bond move away with the new nucleophile or Lewis base. And where the electrons have been removed is our new Lewis acid. So this can happen spontaneously with heat to generate our Lewis base pair. Then if you have enough of a different species, they can then react with something else. So, but the first step in this is that breaking the bond. This is really common in our two-step mechanisms. The first step is going to be breaking the bond like this. And then the next step will be our new Lewis acid reacting with something else. Okay, so those are the 5 things we're most likely to happen in the mechanisms we're going to be discovering over the rest of the semester. Okay, so you might want to put those 5 things into a list of things to remember. Okay. All right. So let me do actual chemical examples from different reactions that we're going to be learning today. Okay. So one of the reactions we're going to learn with alkenes is that you can add water across the double bond, which means when you add water across the double bond, you're going to get an OH on one side and a hydrogen on the other. And you've broken that double bond. And so you only have sigma bonds now. Okay. So the way this happens is actually 2 steps. Okay. The first step is we're going to add a proton. Okay. And so when we add a proton, we use the electrons in the double bond as the base. It's going to reach out and grab a proton away from an acid. Notice this is the hydronium ion. It is already protonated. And when it does that, it generates the new bond with the electrons, but that leaves a charge on one of those 2 carbons. Okay, we have generated a Lewis acid from the system. Okay, and we have a, oops, where'd it go? And we generated our neutral species. So now we have this that is an issue because now we have a Lewis acid and a Lewis base, and that means we can go back and forth. That's what this double arrow means. It means that it's in equilibrium. Okay, so our pattern 1, which is the adding a proton, and our pattern 3, which is a reaction between a nucleophile and electrophile, Lewis acid, Lewis base. Those are the 2 things that happen. This is pattern 1. This is pattern 3. Okay. So, and so that's one thing we can do with an alkene. Let's look at a different mechanism here. Let's look at the other part of this. Let's say we wanted it to react with, now that we have that nucleophile and that electrophile, what's going to happen? Okay. When we see that happen, we're actually going to use this lone pair on the oxygen to go and attack that Lewis acid to generate a new bond. Notice we started with a carbon double bond, and then we added a proton, and now we only have carbon-carbon single bonds. Okay. Now we have our new nucleophile generating a new carbon-oxygen bond. Okay. So this is the difference between the back reaction, which is just transfer of a proton, and this reaction here, which is the reaction of a nucleophile. Now notice, this is very fast and forms this species here. But this species is not done. It's not neutral. So eventually we'll have to do something else with that to finish the reaction. But the key step here is this is step 3, the reaction of electrophile with that nucleophile generated to generate our new carbon-oxygen bond. Okay. So we can also do pattern 2 in this mechanism. In the second step of our mechanism right here, we formed this new axonium ion. And remember, it's a charged species, okay? So the key here is that we need to go ahead and turn it into a neutral species. So the way we do that is we use pattern 2 and we take a proton away from our charged species, and that way we generate a neutral organic compound here, right here, and we've regenerated the acid we started the reaction with. So that is a great thing to do whenever you regenerate the acid to start with. So our first step was adding a proton. Then we had pattern 3, which is nucleophile reacting with an electrophile. Then we had pattern 2, where we removed a proton to generate a neutral organic species. Okay, so when we do this reaction with halogens, we can actually add chlorine or bromine across that double bond. And when we do that, what we have is the reaction pattern number 3. We have an electrophile and a nucleophile forming a new covalent bond. In this case, because bromine is more electrophilic than carbon, it's the electrophile. And because that carbon-carbon bond is less electrophilic than the bromine, it is the nucleophile. And so the first thing that happens is we actually end up having these electrons reach out and displace a bromine off of it. And then these electrons act as a nucleophile. So we have a negatively charged bromine, which is the nucleophile, and a positively charged carbon, which is our electrophile. And they form another bond. Okay. So that gives us this as our intermediate here. And then we have another step, and that it reacts to form the next part. Okay. So the second step on that is, again, pattern 3. We now have a positively charged this bromonium cation that's in a ring, a 3-numbered ring. And now we have a positive charge on here. And so it turns out the bromine right here could attack up here at the, whoa. Okay, could attack up here at the bromine, but that would just go back to starting materials. So, but when the bromine comes and attacks one of the carbons to generate a new sigma bond, it has the electrons, it attacks the carbon. These electrons pop back up, and now we have our bromine with a full octet, our bromine with a full octet. And so we've been able to generate this new system. Not only that, because we form this intermediate, we can predict the products. And we'll talk about that in another goal. Okay, so that was pattern 3 used in a real reaction. Let's look at pattern 4 used in a real reaction. So if we have an alkene and we've added water across that alkene, we've added bromine 2 or chlorine 2, across that double bond. One of the other things we can do is we can add an acid across that double bond, okay? And so imagine you have HCl or HBr. You can add those across the double bond as well, okay? Now, in that step, it's a 2-step reaction because we transfer our proton first. And then but what we can have happen is if we transfer the proton to either one of these, what's going to happen is we'll get rearrangement. This intermediate carbocation is going to rearrange to make the most stable product. And therefore, if that intermediate carbocation rearranges, we're going to end up with some product of the first form carbocation. But most of it's going to be based on the most stable product. So let's look at that rearrangement in stepwise. So the first thing we do is pattern 1, we add the proton. When we do that, the electrons from the double bond are reaching out and forming a new bond with hydrogen, and the electrons go back onto chlorine. So now we have chloride ion as our nucleophile. But we have this carbocation. Okay, so as it turns out, a carbocation stability goes up the more carbon you have attached to it. So if you have one at the end of a chain, it's less stable than one that has 2 carbons on it, which is less stable than one that has 3 carbons on it. Okay. So we'll talk about why in another goal. But the idea is that because the tertiary carbocation, the one with 3 carbons on it, is more stable, it's going to rearrange. And in this case, it's moved a whole methyl group over to there to give us this species. So that's our pattern 4, our rearrangement. And then what's going to happen is we now have our Lewis acid, and we have our Lewis base, and our next step of the pattern is going to be our reaction with the electron. Oh, that's not it, sorry. Okay. So we rearrange this bond, and we're going to have attack by that chloride ion to give us our final product. So then in this case here, we moved a methyl group, okay? But that's not the only thing we can move in these rearrangements. We can also move just a hydrogen. And in the case of this system here, when we protonate this end, we generate a carbocation here. But we have a hydrogen on the carbon next to it, right here. And so what's going to happen is that the hydrogen is going to move over one carbon, and we're going to have our carbocation be on the more stable carbocation, and then we end up reacting it with water in our next step. Again, so in this one, we're moving a methyl group. This one, we're moving a hydrogen. Hydrogen moves faster. You never move anything other than a hydrogen or methyl group. Okay. All right, so pattern number 3, just a straight out nucleophile electrophile. So instead of forming a carbocation to form a nucleophile or an electrophile, we can actually have a compound like this species here. This is boron. This is called borane because it's boron with 3 hydrogens in it. And it doesn't have a full octet, okay? And that's okay. It can just fill up those orbitals to generate this trigonal planar thing. However, because it doesn't have a full octet, it's willing to accept electrons, which makes it a Lewis base. I'm sorry, Lewis acid. It's willing to accept those electrons. So in that case, we have the lone pair of our double bond here. These electrons are the nucleophile. They want to find that positive charge and make that new bond. So in this particular mechanism, we have this pattern 3, the electrophile and the nucleophile attack. And when they do it, it actually does in a specific pattern where the boron is going to be like the proton. It's going to attach where the proton would have attached, because that would be the electrophile. And this hydrogen, as it turns out, is going to be coordinated with that newly forming positive charge on carbon. Okay. So that means that we're going to actually, this is our favored transition state on this, because the boron is acting like the hydrogen. We're always going to add the hydrogen in a certain place as we go through. All right, here's another type of electrophile nucleophile mechanism we're looking at. So in this case here, we have cyclohexene, right? And so the double bond is going to act as the nucleophile. It has the electrons to react. And we have hydrogen, which is actually a neutral species. But when we add a metal catalyst, that hydrogen bond, the hydrogen-hydrogen bond breaks and they bond to the metal. And that gives it a polar bond, which makes it an electrophile. And because of that, we can get this addition of this hydrogen, which is a nonpolar molecule, across this double bond to give us our final product, which in this case is a fully saturated hydrocarbon. All right, and our last example I want to do of the nucleophile electrophile is when we take acetylene and pull one of the protons off with a very strong base. Okay. That creates an anion at the end here. Okay, so that means this anion is our nucleophile. We already have the electrons on the carbon, and it's willing to go out and attack something else. In this case, this is what we call a displacement reaction, because the electrons are actually coming in to attack a polarized carbon and kick out the other species. Okay, this same pattern is still an electrophile nucleophile reaction. It's just it's acting as this anion is the driving force. We're not waiting to form a carbocation. We're kicking this chloride out as a charged species, and we're forming our new carbon-carbon bond. Okay. We're going to see this mechanism a lot, especially in chapter 7, where we have alkyl halides. We're going to see this, this particular mechanism happen again and again and again. Okay, so I've shown you that you need to look for 5 different things to happen in the mechanism. And I've shown you some real world examples of that, okay? Any questions on the 5 patterns to look for? Because if not, we're gonna go and actually look at each one of those reactions in detail and see how it works and what kind of products we should expect from them.
So, Professor David.
Yes.
So, realistically, I mean, that was a lot of examples pretty quick, but going through those and just being able to like recognize one of those patterns is recognizing one of those patterns lead on to another one, or would you just say it's a good idea to just be able to recognize one of them right off the bat?
At the beginning of any reaction, one of those 5 things is going to happen.
Okay.
Think about it is, if you have an acid as a catalyst, you should expect to see number 1, proton being transferred. If you have a base catalyst, you should expect a proton to be taken away. If you don't have an acid or a base, you only have things with electrons and things without electrons. Now you're looking at pattern 3, nucleophile, electrophile. Pattern 4 only happens when you've already formed your carbocation, and it's just going to rearrange to make it more stable, right?
Yeah, that makes sense.
Okay, so you're looking for the different things. They all do different things, and when we go through the reactions, I'll say, oh, it's acid catalyzed, so what's the first step? And
first one.
Right, so it'll follow through, okay?
Okay, yes, sir.
But I wanted to see these and start getting familiar with them so you can recognize them in in our goals number 3.
Appreciate it.
All right.
Thank you. Appreciate it.
So let me go ahead and pull up our goals number 2. Now our goals number 2 is carbocations. Okay. Now I said I was going to explain why carbocations are special and important. And that's what we're going to do in this goals chapter. So the key to a carbocation is that it is a carbon with 3 sigma bonds and an empty p orbital, meaning it lacks electrons, meaning it has a positive charge. Okay. So that being said, all carbocations are electrophiles. They're always looking for that next bond. All carbocations are always Lewis acids. They're always ready to accept an electron pair. Okay, so that's the important thing about the carbocation, is that it will always react as an electrophile / Lewis acid. Okay. Okay, so if we look at the structure of it, the structure of the carbocation is trigonal planar. Okay, and if we think about that, we have sp2 hybridized carbon, right? So our sp2 hybridized carbon is trigonal planar, and it has 1 p orbital available for bonding. In a double bond, we would use an electron to make the pi-pi overlap to make a pi bond. However, in the carbocation, that p orbital is empty. Okay, it still exists, but it's empty. It does not have a negative, it does not have an electron in it, therefore it has a positive charge. So this structure of the carbocation is very important in the fact that it is trigonal planar and you have a place to be attacked on the top or the bottom, doesn't matter. It's an empty orbital. It's going to accept electrons on either lobe of the p orbital, okay? So that being said, if this is what is its stable form, why does having different things added to it make it more or less stable? Okay, so the trend is a carbocation is more stable the more substituted it is, okay? So that means that our tertiary carbocation, the one with 3 other carbons bonded to it, is the most stable. If we only have 2 carbons on it and a hydrogen here, think about that. The hydrogen really doesn't have much of electron density to share or help support that positive charge. Okay, so it's less stable. Our primary right here is something like the ethyl cation here, where we have 2 hydrogens and only 1 carbon to help stabilize that positive charge. And the least stable is what we call the methyl cation. Okay, so they are very hard to make and very reactive. So anytime you have one of these, they are all going to try to rearrange to give us a tertiary carbocation if at all possible, because it's more stable. So what this means is in most of these reactions, when you form a carbocation, you will have this two-step type reaction diagram, where the first step is going to be generating your carbocation by breaking a bond, and your intermediate is the carbocation. Then it's going to react as a Lewis acid and then go and make products. Okay, so let's apply that to our mechanistic patterns here, okay? So once we form that carbocation, it's trigonoplanar and it has an empty p orbital above and below. It's just looking for electrons, and therefore it's going to form that bond, either the top or the bottom, to give us our product here, to form our new sigma bond. Okay. However, if you have the, let's say the thing you pulled off to make your carbocation was in a secondary position, you can move that hydrogen one carbon over, or a methyl group one carbon over, to form that tertiary carbocation set. So notice that there on this one here, this has two hydrogens on it and only one hydrogen on it and two carbons bonded to it. That makes it a secondary carbocation. Okay. So just by transferring a proton from one carbon over, that allows this now, this has 1, 2, 3 carbons on it, to give us a tertiary carbocation. And it has everything to do with the idea that the carbons, each of these carbons, can help stabilize that positive charge by donating a little bit of electron density. Hydrogens can't donate that much electron density because they only have 2 electrons. The carbons have that 8 electrons in their outer shell, and therefore they can help stabilize that positive charge. Okay, so how do we make carbocations? Well, we make carbocations with pattern number 5, okay? And we typically make a carbocation using a polarized bond and heat or light. By exciting that polarized bond, you can break that bond apart. There's a couple different ways to break it apart, but in this case, when we form the carbocation, we do what we call a homolytic cleavage, meaning both electrons go away with the bromine, leaving the positive charge on the carbon. Now, bromine likes having a negative charge because it's a very electronegative element, so it's stable to do this as well. Okay, so think about it as, especially if you can form a tertiary carbocation and you have a polarized bond, it'll break apart. Now, the next step in the reaction is having it react with something else with a lot of electrons. And so you can drive the reaction. It can react with a number of different things once you form this carbocation. Okay. So let's think about carbocation stability, okay? So if you were to take this alkene here and you wanted to add water across that double bond, it could add across that 2 ways, right? The first way would be to add the hydrogen to the end here. And the second one would be add, which would be here. This is adding the hydrogen to the end. The other one would be adding the hydrogen to the middle. So you can add it to either side of that double bond. Okay. However, when we run the reaction, we see this is our product and not this is our product. Okay. So let's look at why. Okay. So in the case of this species here, let's draw it out here. If we have our lone pair here, it reaches out and grabs a hydrogen to make that intermediate, to make that new bond here, we end up with this carbocation as a secondary carbocation with our new hydrogen. Now our carbocation can react with water to make our new carbon-oxygen bond. Okay, so that's a secondary carbocation, so that's probably going to work okay. Okay, what if we added it to the other side? Instead of adding it to this side, what if it added to the other carbon first? What if we added the hydrogen to this carbon first with these electrons, and the carbocation was here at the end? You see that that carbocation at the end is actually a primary carbocation and is much less likely to form than our tertiary carbocation. Therefore, it is not formed in the reaction because it would not add that way. It would want to add to where the carbocation is on the secondary carbon or tertiary carbon as possible. Okay, so carbocation stability is the driving factor for which proton leaves to generate the most stable carbocation, but also after it rearranges what your final product will be. It will be the product that is generated from the most stable carbocation possible. You can't always generate a tertiary carbocation, but if you could, you will. Okay, so let's see another demonstration of that. And when we add HCl across that double bond, the first step is, again, that transfer of a proton. And when we do that transfer of a proton, we will see in this particular case, when we have a tertiary carbocation, a tertiary carbon here, a secondary carbon here, and a primary carbon here. When we add our hydrogen to it, it's going to add to that primary carbon to give us our secondary carbocation. But our product actually has the chloride moved over one. Okay. So we had a competition. We had a intermediate that looked like this carbon right here. And it decided that, oh, I would be more stable if I moved this methyl group over. I could form a carbocation here and make this molecule look a little different. So now that my carbocation is here, this is a tertiary carbocation, and now I can react with my electrophile nucleophile to generate this as my final and major product. Okay. So, questions about carbocation stability? When it can rearrange to make a tertiary carbocation, it will. And you only move hydrogens and methyl groups. Nothing else will move. And hydrogens tend to move faster. Okay. So let's look at how that kind of would affect a certain reaction. So if we have this alkene here, and I'm going to redraw it to look like that right there. And then, so we have a methyl group coming off here, a methyl group coming off here. Then we have our alkene here. And of course, our first step is going to be that addition of hydrogen to that alkene. And so that's going to give us this species here. And I'm adding the hydrogen so you see where it is. Okay. Now, we can't transfer a methyl group from there because if we did, we'd end up with a secondary carbocation. But we do have a hydrogen here. And so if we transfer the hydrogen over here and put the carbocation there, we'll end up with the carbocation in the tertiary position. And our hydrogen has moved over here. And during that transition, we now have a more stable tertiary carbocation. And so now that's where our lone pair on water is going to react to give us our final product. Questions on that? Okay. you see that in these reactions we can use a bunch of different nucleophile electrophiles like water, HCl, hydrogen. So, but it doesn't matter which ones we start with. They all react the same, knowing that it's that formation. One of these 5 steps forms, and we can predict the products based on that. Okay, now one of the other strange things that carbocations can do is they can move a methyl group, technically, and in the case of rings, because the ring has strain on it, because as you take it out of 120 degrees, out of the 109 to 120 to, these are at 90 degrees right here, that makes the ring less and less happy because it wants to be at that 109 degrees. So we call that ring strain. Now, one of the cool things about carbocations is they also release ring strain. If we formed our carbocation here, what's going to happen is this bond is going to move over here and give us a new 5-membered ring. And in this case here, we have 2 5-membered rings. And then when we form our carbocation here, it's going to move over and give us a 6-membered ring. And the 5-membered ring is still intact. Okay. So this is a carbocation rearrangement of rings, but it only happens to form 5 and 6-membered rings. Won't form bigger, won't form smaller. 5 and 6-membered rings are the only 2 things you're going to form from this rearrangement. And there's 2 blank pages there for some. All right, so in summary, okay, sp2 hybridized trigonal planar with an empty p orbital above and below the plane. Tertiary is more stable than secondary, is more stable than primary. We hardly ever see primaries or methyl, so we almost never see them. You can get them in like vapor phase and stuff like that, but we hardly ever see them. Carbocations are stabilized by the fact that we have those carbons donating charge to that central carbocation, and carbocations can rearrange in a 1-2 shift with methyl groups and hydrogens, or to expand a ring to 5 or 6 members. Okay. So when we have carbocations as intermediates, we look for the 1-2 shift to get the more stable cation. We also look for the addition of the nucleophile to form that new covalent bond. The chlorine, the alcohol, the whatever. Okay. And the loss of a proton to give the alkene, which is the reverse step, is occasionally, like loss of a proton is the reverse step is also very commonly seen in some of these reactions as well. All right, questions on just carbocations. This was all about carbocations, what they look like, and how they move around.
Can you go over again that slide where you added HCl to the carbocation?
All right, yeah. So let's just rewrite the whole thing right here. Okay, so there's 2 ways to do this, and the simple way is to look at an alkene right here plus HCl. So the simplest step of the reaction is we're not going to have a rearrangement, and we're only going to have that reaction happen first. So the first thing that's going to happen is we're going to add a proton, okay? Which means these electrons are going to reach out and grab at the proton in the acid, okay? So that being said, if that reached out and formed the new bond here, that would give a primary carbocation, okay? So we're not going to do that. So that means it's going to reach out here and form the new bond on this carbon to give us our secondary carbocation. So we have our secondary carbocation plus our hydrogen. And what's left behind is this bond that was here, these electrons go on to chlorine. And so now we have chlorine with a negative charge. Okay. So the first step in the addition of HCl to the alkene is transfer of a proton. When we did that, we generated our carbocation. Now we have Lewis acid reacting with Lewis base to form a new carbon-chlorine bond. Leave that hydrogen there and give you your chlorine here. So now we have a new sigma bond created, and that's pattern number 3. Okay? So that's the simplest form of that. Now, the alternative form of that is, can it rearrange? Okay? So let's do this alkene with, let's do HBr this time. I'll even draw the bond. So when this comes out, it's again, we have a choice of a primary or a secondary carbocation to be formed during that first proton transfer. Excuse me. Now, after that first proton transfer, we have hydrogen here, we have a bromide ion here, we have a carbocation here. Okay. So we have a secondary carbocation. But if we moved the hydrogen from here to there, we could have a tertiary carbocation. Okay. Tertiary is more stable, so we're going to move that hydrogen one over. We're going to move that carbocation over one carbon. And now we have the bromide ion still here. And now we still have our Lewis acid. So our last step is going to be reaction. Our Lewis base with our Lewis acid to generate our final product, this addition. Notice our original double bond was between these two carbons. But because of the transfer to the more stable tertiary carbocation, our bromine actually added one carbon. Okay, does that make sense?
Yeah, that does make sense. I guess I just didn't see the connection between the primary to tertiary, but once you showed the little intermediate step, it made sense.
Okay, great, great. All right, so that is goal 2. So let's see, we have time, perfect. All right, we're on time for goal 3. All right, now we're gonna take those 2 goals and add them together to look at actual chemical reactions and what their products will be. So we had to know the steps that we had possible, and now let's look at the reagents and how by adding the reagent we change the product, okay? So we are gonna look at just the reactions of alkenes in particular, and looking at how we can add stuff across those, okay? Most of these rules apply to adding them across triple bonds as well. But let's look at just alkenes to keep it simple. Okay. So we have a wide variety of things we can do, and they all basically go through these same steps, and they end up doing the same thing. They get rid of the double bond, and you form 2 new sigma bonds. So if we have HCl or HBr, if we have an acid right here, we call that hydrohalogenation because we're adding a hydrogen for the hydro and a halogen for the other part of the acid. So this is just adding acid across the double bond, hydrohalogenation. The next thing we have is what we call hydration. Hydration is where we add water across the double bond. Okay, so we just add water across the double bond. So one hydrogen is going to go on one side, and then the OH is going to go on the other side to give us our alcohol as our product. This is called hydration. Okay. So hydrohalogenation, adding acid, hydration, adding water. The next one, halogenation. We're going to add 2 halogens across that double bond such that the first carbon has one halogen on it and the second carbon has the other halogen on it. And this is most commonly done with chlorine and bromine. It can be done with other things, but these are really the most common. And the trick here is we're going to add 1 to each side, and they're going to show up at a specific place because of the intermediate form. Okay? Now, another thing we can do is what we call hydroboration. Now, hydroboration is where we take a different Lewis acid and we add it across the double bond. Now, we typically move forward on this reaction and take off this boron and add water and add OH there. However, the first step is the hydroboration. And the first step is key because that's how it adds in a specific pattern. And then the last thing we have is what we call hydrogenation. We're going to add hydrogen across that double bond. This is typically done with a catalyst and typically done with a little bit of pressure, but it's just a way to take our alkene all the way down to the alkane. Okay, so all four of those are going to follow one of those 5 patterns, and they're going to have a selectivity about how they're going to add. So right now we have to think about what's being added, what the intermediate is, and how does that determine the selectivity of the product. All right, so in the case of halogens and the adding acid across it and water, we have a specific pattern right here. We're going to end up with the bromine. Oops, let me go to a different color here. Red. We're going to add the bromine, which is ends up being our Lewis base in part of the reaction, or our hydroxide, which also ends up being our Lewis base in the reaction, to the more stable carbocation. So we're always going to see the hydrogen add to the end. Okay. In the case of the halogenation, it's symmetrical. You ended up adding one to one side and one to the other. So let's talk about the mechanism step by step on how we get to that pattern and what the regioselectivity would be. So if we just added HCl as a gas across ethylene as a gas, okay, what we'll see is the hydrogen's going to end up on one side and the chlorine's going to end up on the other, and we're going to lose our double bond here. And so this is the simplest reaction here. We take ethylene, which is, or ethene as in iupactane, and we're just going to put one on one side and one on the other to give us our simplest compound here. This particular one is called chloroethane. We're going to learn more about naming halogens in chapter 7. Okay, so because that molecule is symmetrical, we don't see the intermediate necessary to make this happen. Okay. But this reaction is what we call regioselective. Whoa. Sorry, I muted there. Oh, well. Okay, is regioselective, meaning the hydrogen's going to go in a specific location and the other part of it's going to go in the other location. And we call this Markovnikov's rule. Okay, what Markovnikov's rule says is that if you have hydrogens on carbons, the hydrogen will always be transferred to the carbon with the more hydrogens. Okay, so if you already have hydrogens, you're going to get that hydrogen. If you don't have hydrogens, you're going to get the other part, the chlorine or the bromine. Okay. So that's what we mean by regioselective, is the hydrogen is always going to add to the least substituted carbon, and the other component is going to add to the more substituted component, Markovnikov's rule. Okay, interesting rule. Do I have to remember it? Yeah, but I'm going to explain why it works. The reason it works is because of the stability of the carbocation here. Okay, so let's look at this as an example here. Okay, again, water, because we're transferring a proton first, is going to follow Markovnikov's rule. Okay, so it's like an acid base. It's like adding HCl across it, but the OH is now the anion that we're forming, and it reacts with the system lines. In the case of something like this with propene, we're going to have hydrogen add to the end of the compound, and our OH is going to be where the secondary carbocation would have been formed. Okay. In this example here, we actually have no hydrogens on this carbon here and 2 hydrogens on that carbon here, which means the hydrogen is going to be transferred to this carbon because it already has hydrogen on it. And the other part is going to be added to the other. Notice that this would immediately form a tertiary carbocation upon the addition of hydrogen. This would have a secondary. So the whole reason Markovnikov works is the fact that you're forming the more stable carbocation during the first step, that transfer of the hydrogen. Okay, so let's look at that stepwise. Let's add something else across it, stepwise, just to see if it can work, okay? So this is similar to what we call similar to a hydration, except instead of water, we're going to use methanol as our reagent, okay? So the reason this works is that we can do all the same steps that we were going to do before and just have a slightly different Lewis base do the attack. Okay? So this is our reagent right here. And when we have acid in there, we're going to transfer a proton to the methanol to give us this cation. Okay, so this looks a lot like hydronium ion, right? Except that it has a carbon-oxygen bond on it. Okay, so it's going to react like hydronium, and it's going to transfer. These electrons are going to reach out and grab this hydrogen. These electrons are going to go back in, giving us neutral methanol. Okay, when it does that, we end up with a tertiary carbocation, CH3, because this has 3 hydrogens on it now, CH3, CH3, plus OME, I'm sorry, H3, lone pair, lone pair, lone pair, lone pair, and a hydrogen. Okay, so these are the products of this reaction right here. Okay, so now we have a carbocation, Lewis acid. We have something with lone pairs on it, Lewis base. These electrons are going to go and attack that carbon. So the intermediate there is going to be, this is that pattern number 3, nucleophile, electrophile. Right, and we still have one more lone pair there, but this lone pair was used to make that bond. Okay, so now we have a charged species. Okay, so now we're going to use number 2, and we're going to lose a proton, and in this case, we're going to lose it to another equivalent of methanol, or maybe to something else like the sulfur ion, and bring these electrons in to give us our product, which is this, oops, sorry, CH3, our ether here. Okay. The steps are exactly the same as with hydration, except we're forming it with a carbon-oxygen bond already on the system. Okay, so we can form alcohols with this, with just using water, but we form ethers when we use alcohols. Okay, questions about hydration. Okay, in hydration, you always end up with water acting as your nucleophile, your carbocation acting as your electrophile. All right, now, in the case of addition of chlorine and bromine across a double bond, we also have regioselectivity, okay? And what we mean by that is that the bromines are going to be trans or opposite each other because of the intermediate we're forming, okay? So if we looked at this, it's easier to see this in a ring system here, because once you add a bromine to the top of the ring, the other bromine has to hit the bottom of the ring. And if it does that, that means we're going to have them opposite each other, completely opposite each other, and we're going to get to the trans configuration of our bromine. Okay. So that's its regioselectivity, but why? Oh, come on, I didn't draw that? Okay. The reason is that there's an intermediate when we first take our double bond and react it with the bromine here. It forms a bromonium cation in a ring. And this ring here means the other bromine can't come at the top to form that new carbon-bromine bond. So they have to come from the bottom to form that new bromine bond. And that's what gives us our trans configuration. Okay. So let's look at the next reaction, that reaction with boron, and see why it's regioselective as well. Okay. So in the case of boron adding, it's regioselective, but it seems to break the rule of Markovnikov's rule. Okay. But it really doesn't. Okay. In the case of these boron substrates, the boron itself is the Lewis acid, and therefore it is going to attach to the least substituted side. In the case of adding hydrogen to it, it attached to the least substituted side, or the one with more hydrogens. Boron's going to do the exact same thing. The boron is acting as a hydrogen in that case, and it's going to add to the least substituted side. Okay. The other cool thing about boron is because we have an intermediate of boron, and this hydrogen is going to be getting lined up with that double bond. This is going to go to the least substituted side right here, and then this is going to go to the more substituted side, but they're going to transfer at the same time. So that means the boron and the hydrogen are going to transfer on the same side of that double bond. Okay. And halogens, they're opposite sides of that double bond. In boron, they're the same sides of that double bond. Now, if you form a carbocation, it can be either side. Okay. So when we do reductions or add that hydrogen across the double bond using a catalyst, this also adds on the same side because your hydrogen has to break apart on the metal surface. Then your alkene comes down and both hydrogens are transferred to the same side of there. So that means our hydration reactions are also syn addition, or adding to the same side of that double bond. And do I have only alkynes now? All right. So I thought I had a summary slide that told you about syn addition versus anti-addition versus mixed. And there is one in the book that gives you an idea of if you add a hydrogen first and wait around for a carbocation, you're going to get a mixture of addition at the top and addition at the bottom. Think about it. Every time you have a carbocation, it can be attacked at the top or the bottom. If you form an intermediate that forms a three-membered ring with boron or chlorine, you have to have trans addition. It has to come in from the other side. Anytime you have boron or catalytic hydrogenation, you always get syn addition. It always goes to the same side. So those are the three different types of addition you can get: mixed, syn, or trans, and the three different reactions that do it that way. All right, the last thing, because I have about 5 minutes, is acetylide ions. Okay. So we said that hydrogen on acetylene is acidic. And if we use a very strong base, like in this case, sodium amide, right here, it can pull that proton off and make ammonia, which is the weaker acid, and gives us this acetylide ion. That ion, in this case, is acting as our nucleophile. And in this case, it can displace a bromine to generate our first intermediate here. Now, in our first intermediate, we still have an alkynyl hydrogen. We still have a hydrogen on that triple bond. So we can actually take that off again and react it with something else. And notice it gives us an unsymmetrical long chain alkyne. We started with 2 carbons here. We added 2 carbons to give us 4 carbons. We added 3 carbons to give us a total of 7 carbons now. And all we're doing is reacting using the acidity of these hydrogens on the 2 ends and doing it stepwise to get an asymmetrical alkyne. Okay. Now, just like alkenes, we can use that catalytic hydrogenation to reduce them down to alkanes, okay? Now, the key here is that if you use the same conditions, you can't stop at the alkene because the alkene is just as reactive as the alkyne to this catalytic hydrogenation with hydrogen, palladium, platinum, or nickel. Okay? So there's no stopping the system. The only way to stop the system is doing what we call Lindlar's catalyst. Lindlar's catalyst is where we actually take the catalyst and we poison it with lead, sometimes called poison catalyst. And basically, by adding that other metal there, it deactivates the surface slightly. And so when it deactivates the surface, that means the alkyne will come down and adhere to the surface and get syn addition, get 2 hydrogens added to it, but now it's not reactive enough to add across an alkene. And therefore, once we poison the catalyst, it won't react with alkenes, and therefore we can actually get alkenes from alkynes, but they're always going to be cis alkenes because they add across the same side of the triple bond. Okay, no, I'm not going to do those. All right, we're out of time anyway, but these are all different reactions that I go through on the videos. If you want additional problems, those are on the set as well. And similar to these, similar questions are also in the homework that are due this week. All right, questions about Chapter 5. These are the different reactions and reaction mechanisms associated with alkenes and alkynes.
Professor?
Yes.
How would you phrase a question about this?
Well, things would be like, what would be the major product of adding HBr across this alkene? And so what you would look for is to put the hydrogen where more hydrogens were, put the bromines where the less hydrogens were. Or look if you could form a tertiary carbon, you might have a rearrangement. Another one would be starting with this alkene, where would the carbocations form and would they rearrange? You know, things like that, okay?
Okay, thank you.
And the wording of the questions in the quizzes are, I mean, in the homework are very similar to what I use on the exam.
Professor David.
Yes.
So probably don't know why I'm saying it's not really a question, but like by seeing all of these little factors and being able to recognize them, like you were saying, that's like your checklist that you can use when you're trying to figure out what it is, correct?
Yes. So if you're trying to figure out the mechanism, you're looking for these 5 things. If you're looking for products, what you want to look for is, if the reaction forms a carbocation, then we're going to have a mixture of them adding on the same side or opposite sides. Certain reactions always add opposite, and certain reactions always add on the same side. Those are codified in the book in a table and in the slide, the big slides.
Okay. And then you were talking about cis and trans too, so it's definitely pretty important to kind of keep that in mind as well, right?
Correct. Cis and trans for alkenes, for sure, for naming, but then that cis and trans configuration is only attributed to cyclics because you don't have free rotation. But it demonstrates that they have to be opposite each other. That's why I use that as an example.
Okay. Thank you, sir.
Okay. So I'll go check and see if there's a group meet. I'm not supposed to set up a group meet because I'm not supposed to monitor it. So I'll go see if I can get one set up on the announcements page of the Canvas. So I'll go look into that right now. Okay. All right, I'm gonna go ahead and stop recording. If you want to ask questions, we still can.